Alright, so hemoglobin
Good morning to you.
has 4 subunits, which means it has a quaternary structure. So, quaternary structure, last class we did primary structure is the sequence, secondary structure are the alpha helix beta sheet, and then tertiary structure is the final structure of the protein. And everyone can hear me at the back, right? Okay. So, because this has a larger volume also if you want.
Is it on?
So,
Yeah, can you make it louder?
alright, so the quaternary structure means more than one protein chain bind to each other. And when we did that last class, we did not really look at what forces bring them together. Now, since hemoglobin is a tetramer, it has 4 subunits, which means 4 protein molecules are always together. So before we continue with the hemoglobin, let's go back to the previous chapter and understand why 2 subunits or 3 subunits come together. What is the type of interaction between them that brings them together? And it is the same type of interaction that we studied. So those are the ionic interactions. That means charged amino acids will bind to charged amino acids. So most likely then when 2 subunits come together, they have charged amino acids like a lysine with a positive charge, aspartate with a negative charge. Then the 2 subunits may come together and interact, and that's why they are together. So that brings us to another question. When we did the amino acids, remember the amino acids, lysine, arginine, these are basic amino acids. Whereas aspartate, glutamate, these are acidic amino acids. That term applies to the free amino acids when they are in a protein in the neutral pH solution, which is always the case for us. The lysine is charged. The lysine is always present as NH3. All the amines are NH3 plus. All the carboxyl groups, so this will be a couple of carbons and then NH3, and a couple of carbons and then CO minus for the aspartate and glutamate. So every acid has a conjugate base, every base has a conjugate acid, so it was an amine before. And that binds to a proton at neutral pH. All the molecules are like this, are NH3 plus. And all the molecules of all the amino acids will be like this from the COOH. And this is a base. This is an acid. So in the protein, whenever we talk of an acidic group, we are not talking about aspartate and carboxylate. We are talking about lysine, arginine. These are the basic amino acids that behave as acid in the protein because we are always at neutral pH. And in the same way, aspartate and glutamate behave as bases in the protein. Alright, so this thing will come again and again talking about acids or bases at some site in the protein, and this is what we mean. Acid means anything that is NH3 plus, base is anything that is CO minus. These came from the opposite amino acids. Bases give acid, acids give bases as the conjugate form. So ionic interaction will be between an acidic amino acid and the basic amino acid in the region where the 2 subunits interact. You can also have other interactions like hydrogen bonding or hydrophobic interactions. The ionic includes the polar, so this is also usually termed as electrostatic. So electrostatic means either as ion or just a polar side chain like hydroxyl group that is polar. You can have hydrogen bonding. OH of one amino acid can hydrogen bond with the OH of another amino acid, and that's why the two subunits are together. You can have hydrophobic interactions. That means all the hydrophobic amino acids are facing one surface of one subunit and facing the other surface of other subunits, and that's why the subunits are together. So these are the forces that bring them together. There is another force that people thought is also involved in bringing the subunits together, and that is a disulfide linkage.
Oh my God.
What is a disulfide? There is one amino acid that has a SH group, and that is cysteine, so which is usually written as cysteine SH. To show that SH is the important group here. So here is one amino acid, one protein molecule that has a SH here, and another protein that has SH here. So these come close to each other and get oxidized. So SH is a reducing agent, easily gets oxidized, and then we are always in an oxygen environment, so they get easily oxidized in presence of oxygen. So it forms a cysteine-cysteine bond. So cysteine, S, cysteine. So this is called a disulfide linkage, and this species, cysteine-cysteine bonded through SS, has a special name. It's called cysteine. Almost in spelling except T-I-N-E, and then cysteine refers to two cysteines bonded together with a disulfide linkage. And disulfides are present in proteins. In many cases, they can be within the protein, like other proteins have all these amino acids, and there may be a SH here and a SH here that are close to each other. So there may be a cysteine, two cysteines in two different regions of the chain, but in the 3 dimension they are close to each other, and they may form a linkage between them. So they may form linkage, intramolecular linkage or intermolecular linkage. The intermolecular linkage may be responsible for keeping the subunits together. The intramolecular linkage within the same protein, two SH groups can combine to form a disulfide linkage. Now, initially people thought this is a driving force for proper folding of the protein to this particular structure in which the cysteines are close to each other. But as I mentioned, Hanfinson's name, Hanfinson did an experiment which is called the Hanfinson experiment. Of course, he got the Nobel Prize for that. We are not discussing that. We are only talking about what his conclusions were from the experiment. So he made two conclusions. One is Hanfinson experiment. One conclusion is that the primary structure determines the final structure. That means the sequence, primary structure is same as sequence. So sequence of a protein determines the final structure of the protein. That means this structure is already pre-decided based on the sequence of the protein. Yes. Hanfinson is the name of the person. Hanfinson. Hanfinson. We are not doing that experiment, but just the conclusion from that experiment is that proteins automatically give you this structure. The sequence itself determines the final structure, and it will automatically have the structure. Yes? Yes. So, Hanfinson experiment conclusion is that protein structure determines the final structure, it automatically becomes that structure. And the second conclusion that he got from his experiments is that the disulfide bonds are not the driving force for the protein to form. It is also not the driving force for two subunits to come together. These two subunits are coming together not because they can form disulfide bond, but because of these reasons. Or this final structure of the protein, this cysteine and this cysteine are close to each other, not because they form disulfide bond, but because of the other interaction that the protein has. The disulfide bond, the two cysteines just happen to be close to each other based on the other interactions. Once they are close to each other, then they can get oxidized and form a disulfide bond between this one and this one. So this sulfur and this sulfur can form the disulfide bond. So the disulfide bonds do form, but they form after the protein has formed. The disulfide bond between two subunits will also form, but that's not what is bringing them together. They form after the proteins have come together. And so what the disulfide bonds do is to maintain that structure. Whatever structure it is, it maintains that, and so that it doesn't move away from that structure. Yes.
Obviously not if this sulfide bond is inside the protein, right? That's not going to be the last thing that's done. Like if it's an intramolecular bond.
Right, that's not responsible for the water-ready structure. Is that what you're asking?
So that's not something that forms after the protein is formed.
That does form after the protein forms, yes. The disulfide bond is not forcing the protein to have that structure. First the structure forms, and then disulfide bond formation is a slower process. It happens later. So that is not the driving force for forming whatever structure the protein has. The protein forms that structure because of these interactions, hydrophobic, ionic, mainly the hydrophobic. Hydrophobic is the most important one. And after the structure has formed, then the disulfide bonds form between them to give you the final structure. So, just as a side note, there are many proteins that have these disulfide bonds. Almost all proteins have them. Maximum number of disulfide bonds you will find in your hair. Keratin has disulfide bonds, and that is actually responsible for the shape of the hair. When you want to get a different shape, you go to wherever you go, and they put some chemicals in it. Basically, you are oxidizing and reducing them. So you are reducing the existing disulfide bonds in keratin, and then giving it a new shape, and then again oxidizing it with another chemical that again forms new disulfide bonds, and then keeps the hair in that new structure because of the new disulfide bonds. So keratin is full of cysteines that can form disulfide bonds to give different shapes. All right, so coming back to hemoglobin, hemoglobin has 4 subunits that are together. There is another protein that also binds oxygen, and that is called myoglobin. So myoglobin is a monomer. That means it has only one subunit, and hemoglobin is a tetramer. That means it has 4 subunits. All the 4 subunits are not exactly the same, but they are very, very much similar. So they are actually called 2 alphas and 2 beta subunits. But the alpha and beta are also very similar. So let's consider them as 4 subunits of similar kind. The function of hemoglobin, as everyone knows, is to transport oxygen. And the function of myoglobin is to store oxygen. So hemoglobin transports oxygen from the lungs to the various tissues in the blood. And myoglobin stores oxygen mainly for the muscles. So this is present in the muscles. So stores oxygen in muscles. Why does it store the oxygen? For those times where your muscles are not getting enough oxygen from the blood. For example, when you are running 100 meters at a very fast rate. You don't get enough oxygen so quickly, so the oxygen then comes from the myoglobin that is already present in the muscles. People who are non-vegetarian and you cook at home, you know that if you cut meat and wash it 100 times and then leave it in somewhere, after some time you find it's still red. Where did that red color come from? That is not blood. We have washed the blood. There was no blood to begin with. The blood was all drained out before it comes to the market. So all that is because of myoglobin that is in the muscles that gradually come out, and that gives the red color that keeps coming out even though you wash it so many times. So the muscles have the myoglobin which stores oxygen. So what is the difference between hemoglobin and storing oxygen and transporting oxygen? The difference is in this. The tetramer, this is extremely important, and this is a monomer, that means one subunit. So one subunit gives it, both of them bind oxygen. Because the tetramer binds oxygen with two different affinities, that is responsible for transporting oxygen. Once again, what is involved in transporting oxygen? In the lungs, it must bind to oxygen. In the tissues, it must release oxygen. So that is the important property of any transport company. As I said, they have to first bind and then release. Whereas hemoglobin doesn't release oxygen most of the time. Most of the time, we are not running 100 meters. So it is there. It is just there for emergency use. So it is always bound to it very tightly and doesn't release any oxygen unless the oxygen level goes down to very low levels. So most of the time it is you get your oxygen from the hemoglobin, which binds oxygen in the lungs, where the oxygen concentration is high, and it releases oxygen in the tissues where the oxygen concentration is low. So let's look at the binding to oxygen. Whenever two things bind, let's say A binds to B. In any sign, when two things bind, there is a binding constant. How tightly do they bind? So that's an equilibrium process. So you can write an equilibrium constant. If it is very tight binding, then equilibrium is more towards the right side. If it is loose binding, equilibrium is more towards the left side. So there is something called the tight binding and loose binding, depending on which direction the equilibrium lies. So when hemoglobin binds, it binds with two affinities, a weak binding and a strong binding. When myoglobin binds, it binds with a very strong affinity. But they are the same molecule, or very similar molecule. And it is the tetramer structure that is responsible for having two different affinities for oxygen. So if you plot a graph of oxygen binding, so let's say oxygen bound or percent oxygen bound at different oxygen concentrations. So in the lungs, oxygen concentration is 100 torr. 1 torr means 1 millimeter mercury. Let's say this is 0 here. Why is the oxygen concentration in the lungs 100? Does that agree with any of the numbers you have studied? Forever. You have always studied that oxygen is what percentage of the total in the air? Close to 20% or close. And what is the 1 atmospheric pressure? How many millimeters mercury is that? 760. So if 20% is oxygen, that means 1/5 of 760 should be the partial pressure of oxygen, which is not 100. 1/5 of 760 will be something like 150 at least. So it should be 150, but writing here 100 is the pressure of oxygen, the partial pressure of oxygen in the lungs. Why is that? Because the concentration of oxygen in the lungs is not exactly same as in the air, because in the lungs you have a lot of carbon dioxide. That's the whole purpose of breathing, you are breathing out carbon dioxide and breathing in oxygen. So in the lungs, there's a lot of carbon dioxide, and so the percentage of oxygen is not what is present in the atmosphere. It is less than that, and people have calculated that it comes to 100 millimeters of mercury. And what is the concentration in the various tissues? It can vary anywhere from 20 to 40, let's say. So depending on the type of tissues, it will be somewhere in this range. So for myoglobin, which binds very tightly, it has one subunit. So as you increase the oxygen concentration, you are increasing the oxygen concentration and looking at what percentage of the molecules are bound to oxygen, and it will be something like this, where this is 100%. That means 100% of the hemoglobin molecules are bound to oxygen. If you do the binding curve for hemoglobin, it will not look like this. This is called a hyperbolic curve. If you look at the binding curve for hemoglobin, it looks like this. This looks like a S shape, and that is called a sigmoidal. So it has a sigmoidal curve or sigmoidal binding, whereas myoglobin is hyperbolic. And the difference results from the fact that myoglobin has one binding affinity. It has a certain affinity, and as we increase the oxygen concentration, it increases, and then towards the end it becomes 100 and stays there like that. On the other hand, hemoglobin initially binds very poorly, so not much binds. By the time it is only bound this much, myoglobin, as you see, has already gone to more than 80%. So if you want to determine the binding affinity, the way, if you are doing an experiment, the binding affinity is determined by drawing a straight line in where it is increasing. So this is the binding affinity here. The slope of this line here tells you the binding affinity. Slope of this line tells you the binding affinity of this one. It's very low. But then there is another slope here. This is a very high binding affinity. So hemoglobin has two binding affinities for oxygen, whereas myoglobin has only one, and that is responsible for releasing of oxygen into the tissues. So let's understand how that happens. So let's say in the lungs, both of them are, myoglobin is not in the lungs, but when you have full amount of oxygen in a certain tissue, in the muscles, then it is all bound. If you don't have that full amount, even if you have 20% of this, let's say 20% of 100, the myoglobin is still about maybe 80-90% bound. So in other words, myoglobin in the muscles is more or less always close to 100% bound to oxygen. Whereas hemoglobin in the lungs is 100% when it comes to a certain tissue, let's say depending on what tissue it may have this amount or this amount. So when it comes to this tissue, it has less binding, so this much of oxygen will be released. So it had this much of oxygen in this tissue. It is supposed to have this based on the oxygen concentration, so this is the extra oxygen that is released. Another tissue that has even lower oxygen amount, then the oxygen binding of oxygen should be here. Let's say instead of 40, it is at 30 or somewhere, where it is supposed to have this much of oxygen, and so this oxygen will be released into those tissues. So whichever tissue needs more oxygen gets more oxygen, right? The one that has low oxygen obviously needs more, and so it gets more. It is the difference between the lungs and this pressure that will decide how much is released. And when in the tissues it is almost gone, all the oxygen is released, of course that becomes deoxygenated blood, and then it is taken back to the lungs and binds again. Myoglobin, on the other hand, is always 100%, only when the oxygen concentration goes down under special circumstances, then it will release that oxygen, depending on how much low the muscle is in the oxygen. And then after that period is over, then again the muscles are getting back the real amount of oxygen normally it gets, even if it is this tissue that is supposed to be at 20% oxygen level, it still binds 180% or more of myoglobin. So myoglobin very quickly becomes oxygenated again, and then it stores that oxygen for the next time. So what is the response? As I said, if it is a tetramer, it has these two affinities. Why does it do that? Why does it have these two affinities? It has these two affinities because of something that binds to hemoglobin and changes the affinity of hemoglobin for oxygen. So in general, if you have a protein, not talking about hemoglobin, let's say you have a protein here, it binds to a certain molecule called S. There will be a certain affinity for binding to it. There is another molecule, let's say called I. If I binds here, it changes the binding of S. So I will be called an effector. It is an effector of oxygen binding. Effector means it can be an activator or inhibitor. So there are some molecules that inhibit binding of something. I'm not talking about hemoglobin, but any molecule that binds to any protein. For example, enzymes bind to their different substrates, and that binding may be influenced by other molecules that either increase or decrease the binding. And that other molecules bind somewhere else. It is not binding here. It is binding to some part else, some other part of the protein, and it is changing the binding here. So in that case, in general, they are called effectors. It can inhibit or activate binding, so they are activators or inhibitors. In case of hemoglobin, it is the same thing. Hemoglobin binds oxygen, and the effector is also oxygen. So this is oxygen binding, and effector is also oxygen. So obviously the oxygen is not binding to a different place, it is binding to the same place. So the effect of hemoglobin is oxygen binding here. That increases the affinity for more oxygen binding. One molecule of hemoglobin binds to only one subunit of hemoglobin binds to only one molecule of oxygen. So if one molecule of oxygen is already bound here, it cannot change the affinity of this one, but it changes the affinity of the other three. As I said, hemoglobin is 4 subunits. So let's say you have, let's draw the subunits this way. Let's draw the subunits like this. Just a symbol. So if this is the low binding affinity structure of the hemoglobin, so this is called the tense form. So hemoglobin structure exists in two forms. One is called the tense, the other is the relaxed. In the tense form, the binding is very poor, slow binding or low binding. And when it goes to the relaxed form, by binding oxygen. So if one of these subunits bind to oxygen, that must be in the relaxed form. So that will be, let's write the relaxed form this way. So this is a very low affinity. It happens, it needs a lot of oxygen to do that. That means you are in the initial part of the curve. You are increasing the amount of oxygen, but the binding is increasing very slow or very little. As soon as this is formed, it changes the conformation of the other three. So immediately, this binding changes the other three to go to the last state. And so these bind oxygen with much greater affinity. So that is this part of the curve here, where one oxygen bound to one of the subunits increases the affinity of all the other subunits to the high affinity form, so that they all bind oxygen immediately, and so that's why the curve increases rapidly here. Yes?
What's the end of that arrow?
Immediately, low affinity. So that arrow is immediate. It switches immediately. When one subunit binds to oxygen with difficulty because the affinity is low, so this binding is not easy, it is slow. Once it happens, it immediately converts these to this form, and they all bind to oxygen regularly. And that's why the curve is increasing like this.
I have a question. So you sent us like a sheet on for the email, and on the sheet on the email it includes the P15 numbers. Are we responsible for knowing that as well, or what is that?
All right, so what percent, whenever you putting bind A and B bind to the AB, how do you refer to what percentage is bound? I wrote them as percent, like 0 or 100 or somewhere in between. In pharmacy, you will always find another way of expressing these, like what percentage of the molecules are doing a certain thing. And that is called the P50. So people are interested in not when it is 100%. As you see, 100, it's not just about hemoglobin binding to oxygen, it's about any protein doing any work. When it goes to 100%, it is increasing very slowly. When it is close to 0, change is slow. Right here, change is significant. And when, as a pharmacist, you are interested in this region, that's where the real thing happens. And you want to classify this as what concentration of whatever, in this case oxygen, gives you 50% activity. So people are always interested, that's a way of classifying the reaction or binding or whatever the protein is doing. You want to know when this 50% happens. For example, if it is an antibiotic, it kills bacteria. You want to know at what concentration it kills 50% of the bacteria. Yes.
Alright, but you have to memorize like the numbers you provided.
You don't memorize anything. If anyone is studying anything by memorizing anything, you have the totally wrong approach. Yes.
Is going from tense and relaxed form an equilibrium reaction as well, or no?
No, it's not an equilibrium reaction. It is called this kind of change when first binding is slow and the remaining binding becomes very fast. That is called a cooperative effect.
That was important. I'm not going to tell us He was not going to tell us.
Well, yes. Cooperative effect you will find not just for hemoglobin binding to oxygen, but many times you will see this. That means initially something is slow, then it is very rapid. That is called cooperative. That means the first event increases the rate of the next events. Alright? You can see that with enzymes also. Some enzymes work like that. Initially they are very slow, and then when it starts it becomes very fast. And how do you tell something is cooperative? You tell that by this S-shaped curve. So sigmoidal curve results from a cooperative process. Or you can say whenever you see a sigmoidal curve, it must be cooperative, or if it is cooperative, it must give you a sigmoidal graph. So this process again is sigmoidal or cooperative because initially it is slow, then it is very fast. Alright, so as I said, in this case, then oxygen binding to hemoglobin increases the affinity of something, so oxygen is the activator of its own binding. In other cases, in some other protein, maybe enzymes, you will find people who have taken molecular biology, who have studied gene expression, there are molecules that increase gene expression and then molecules that decrease gene expression. So they are called activators and inducers. So you will see these terms many times. So in this case, oxygen is an activator of its own binding. Now there are some molecules that inhibit the binding of oxygen. And one of them, so we are talking about inhibitors that inhibit this process. And we'll talk about two inhibitors. One is called 2,3-BPG. And another inhibitor is just acid. So 2,3-BPG stands for bis-phosphoglycerate. If anyone knows the structure of glycerate, it has 3 carbons. It is derived from glycerol. So it has 3 carbons in a chain. And so glycerate, of course, means there is a carboxyl group. And 2,3-bis-phosphoglycerate. So that means there is a phosphate at carbon 2 and phosphate at carbon 3. Bis means 2. Right? Di also means 2, as in ADP, adenosine diphosphate. What is the difference between bis and di? Whenever you see di something, it means they are one after another. The 2 phosphates are linked to each other. So adenosine, then another phosphate, and that phosphate is linked to another phosphate. So that is called diphosphate. Bis means there are 2, but there are 2 different positions on the chain. So one is at carbon 2 and another is at carbon 3. So if I draw the structure, and so this is 2,3-BPG or 2,3-bis-phosphoglycerate, and this has how many negative charges? 5. Right? There are 5 negative charges, and this binds to the hemoglobin. It doesn't bind to myoglobin, it binds to hemoglobin, because in hemoglobin, when you put the force up in it, I'm drawing circles, but they are not, of course, circles. You have the structure or in the handout that I gave you. So in this region, there are 5 amino acids coming from the various subunits that have NH3+. Where does NH3 plus come from? It comes from lysines usually. And every protein has one free amino group. Which one is that? Remember, in a protein, all the alpha amino groups are involved in peptide bond formation, except the first one. First one is not bonded to anything, so that has a free amino group. So there are 6 of these that are represented here, coming from the lysines and coming from the first amino acid of 2 of the chains, and those positive charges, so there are, I'm just writing the positive charges somewhere here, that are involved in binding to the BPG. So that's where BPG binds, by binding to the positive charge of the various amino acids in that binding site. And the binding site is not the same as oxygen. The oxygen binds somewhere here, let's say. If BPG is bound here, then oxygen cannot bind. So BPG, in other words, decreases the binding of oxygen, and that's why it is an inhibitor. The body always, the blood always has a certain concentration of BPG, around 5 millimolar or so. So at different concentrations of BPG, you will have different extent of inhibition. If you have more BPG, there's more inhibition. Less BPG, less inhibition. Why do you want to inhibit binding of oxygen in the first place? You want to bind more oxygen, right? Why do you want to inhibit binding? In fact, you do want to inhibit binding because if it did bind more and more oxygen, then it becomes like myoglobin, it never releases it. Right? So it's not just about binding oxygen. In the lungs, there is so much of oxygen that 100% of the molecules are bound anyway. You don't want to increase that binding anymore because it's already 100% bound. But what the BPG does is lowers the binding of oxygen, and that's why you have this sigmoidal curve. At low oxygen concentration, it has a low affinity because BPG is bound there, and it prevents binding of oxygen to the hemoglobin. That's when you are in this region, somewhere here. More BPG you have, more in this region you will be. That means it has less and less oxygen bound. So that's how the presence of BPG actually is responsible for this sigmoidal curve. It inhibits binding, and then when you go to tissues that have less oxygen, the oxygen will be released, and then it becomes deoxygenated blood, goes back to the lungs and binds to oxygen. When it binds to oxygen, the BPG is released. Both things cannot be bound at the same time. So that's how the BPG controls how much of oxygen will bind, and that is important for hemoglobin. It's not important for myoglobin, so myoglobin doesn't have BPG. In fact, myoglobin doesn't have this pocket here, this site that happens because of the 4 subunits there. So BPG doesn't bind to myoglobin, so it has only one affinity for oxygen, whereas it has different affinities for oxygen in hemoglobin. If you go to the mountains where there are less oxygen, instead of 100%, let's say, instead of 100 millimeter mercury, you go to 10,000 feet or 20,000 feet high, there is much less oxygen and you have difficulty breathing. Why do you have difficulty breathing? Because there is less oxygen. So this curve, let me use a different color. So this graph then will be like this. Let's say this is the maximum amount of oxygen, let's say 80%. So that's what can bind. So you are fresh up the mountain, you go there first day and you want to breathe, you cannot breathe because it is releasing, instead of this much, it is releasing only this much of oxygen. So this tissue or this muscle here needs this much of oxygen, it is getting only this much because it's starting with low amount. And everyone who has done this, you know that you stay there for 24 hours and next day you are fine. You are just working like the native people there and running around. How does that happen? That happens because your body increases the amount of BPG. So more BPG means more inhibition. So when you are in 10,000 feet altitude, your blood within 24 hours adjusts to it and makes more BPG. So instead of this being your oxygen binding, the oxygen binding will be less. That means this curve shifts like this. So it binds even less oxygen. So when the blood goes to this tissue, it is releasing this amount of oxygen. I may not have drawn the graph right, something like this. So it releases this amount of oxygen, which is the same as here. So whatever amount it needs, it releases that same amount because the body adjusts by increasing the BPG. So you are binding less by, let's say, 20%. So it inhibits the binding 20% more, so that eventually you are getting the same oxygen in the tissue. All right. So it takes 24 hours. So if you are a runner and you have a competition somewhere up in the mountains and you reach there, and there are some businessmen who tell you, I give you free airfare to go down and have a good night and then come back, bring you back here. What they are doing is they are just lowering your BPG, and next day when you come here, you cannot compete. So don't take those offers. If you're up there, you have to be there for 24 hours before you start doing anything else. Yeah, otherwise the first day is the bad day for you. Right, and that's the reason. If you are there for months and years, gradually your body adjusts more, and you become like people there. They don't really adjust the BPG like this. They adjust the amount of hemoglobin, amount of erythrocytes, number of red blood cells. All those things are gradually adjusted over a period of months to become a person who lives there. All right, and once again, when you come down, you're again adjusted, readjustment takes place. Yes. So we will stop here, yes. It takes 24 hours for the people to the right level.
They never showed up.